Sunday, November 22nd. Thanks for checking out the video. I'm Jeff Hunter. Just doing a quick review of the past week as we had a number of projects that are starting to come to completion as we get closer and closer to Christmas. And so one of the projects is John Paul II Secondary School in the Catholic District Board in London, Ontario. We were a supplier to Amoresco Inc. in their London, Ontario regional office for a pair of central chiller plants, dedicated heat recovery chiller plants, and a few ground source heat pump rooftop units. And so this was a really exciting project. If you follow my channels, you know, very passionate about geothermal systems. And this was an exciting project as it was an existing building that they are decarbonizing to make carbon neutral. And it's actually Canada's first carbon neutral retrofit of a high school or a school in Canada. So it's pretty exciting. A lot of different renewable technologies being applied at this school: solar PV, battery storage, geothermal, and I hope I'm not missing anything else, but electric car. So off the solar PV, they're also using electric car chargers as well. So a very exciting project, so glad to be a part of it. And Multistack and JPII are well suited to the application, as that's our expertise. Is if you look through our product portfolio, electrified solutions is primarily what we work with. We typically don't work in very many gas applications anymore, although we can. We have a lot of demand in the electrification side of things. So heat pumps and heat recovery chillers and high performance chiller plants is sort of what we do. And Multistack was really well suited to this application because it's a retrofit. And Multistack is the originator of the modular chiller plant. And so this particular application had 2 rooftop penthouse mechanical rooms, and the only way to get in them was to cut a hole in the roof, and it was a pretty small space to get through, but we were able to crane in individual modules of our chiller plant onto the equipment pad and then connect them together right there in the mechanical room, which you'll see some pictures of here in my video shortly. So that was exciting. We have 2 chiller plants in there. One's a low temperature chiller plant that's directly connected to the geothermal loop field. I should say big shout out to Buchanan and Hall out of Stratford, Ontario, that did the directional boring, horizontal directional boring of this loop field that is now resting nicely underneath the racetrack soccer field in front of the school. So the low temperature plant, we connected directly to that, and then we have a high temperature plant which operates off R134A refrigerant, and it's connected onto the building loop. So basically it's a cascade chiller system where the low temperature plant is upgrading the heat from the geothermal loop to the building loop, and then the high temperature plant is taking that building loop water and boosting it to 160, max 170 degrees. And that's because, of course, this is an existing building. It's an older building. And so the distribution system is more of a conventional style system. So the school has perimeter radiation, and that's typically in the area of needing about 180, 170, 180 degree water. So through the analysis, we were able to find that the perimeter loop could get away with 160, 170 degree water. And so that's the point of our high temperature chiller plant. So I won't explain that one too much more because I do talk about it here in my videos, but lots of other stuff going on this week. We had the Ontario Geothermal Association AGM, which I was able to chair, and that was really exciting. We had a great turnout for that. We reviewed, of course, the stuff that you normally review at an AGM, our objectives for the next year and some of the things we've been working on. But we also reviewed in depth a report that we commissioned with HRAI. We commissioned Dunsky Energy Consulting to look at electrification of buildings in Canada, and it was really a complement or a analysis of a previous study that was done last year that the Canadian Gas Association did, which unfortunately forgot to include. I'm not sure if it's forget or just did not include ground source heat pumps in their analysis. And we thought that, we know that ground source heat pumps are a very important tool as we go forward in electrification, perhaps even one of the most important tools. So it was important on our end to be able to put our input in on how ground source heat pumps can help Canada decarbonize and electrify buildings, and the results were very promising. And so we're continuing on with that study into a second phase. So look for the first phase on our website, www.ontariogeothermal.ca, and the second phase we are working on now as well. So without any more chatter there, check out this video walkthrough I did of the chiller at John Paul II High School. And if any questions or anything I can help you with, reach out to me anytime. Thanks. So today we're at John Paul II High School in London, Ontario, and this is a project that myself and JPII have been working on for the last, I guess it started about a year ago, in partnership with Ameresco and their regional office out of London, Ontario. Ameresco was contracted by the school board to retrofit their mechanical systems in this building under an energy performance contract. So what they've done is totally revamped the central plant where we got involved, and then the school has a distributed heat pump loop with heat pumps in various zones throughout the school. So we weren't taking part in that part. Our role here was just on the central plant side, which I'm very excited today to show you what we have in here. So as most of you know who follow my channel, I talk a lot about geothermal systems, and John Paul II School decided to go with a horizontally bored geothermal system beneath their soccer field just out front of the school. Now, this retrofit of this school is very interesting, as if you read some of the early news articles that came out of London about it, they wanted to make the high school really a self-sufficient place where if there was ever a city disaster, community members could go and the building would be 100%, could be 100% off-grid and reliable on its own power sources. And so outside in the parking lot, you'll see a parking lot that's covered by solar PV panels. And then in the building, they chose to go with geothermal heating. And there is a small backup boiler system here that kind of contributes to the design of the geothermal system, in that we're doing peak shaving with those boilers. So to try and keep the size of the geothermal loop down to fit within the landscape of the building, boiler peak shave was introduced to cut down that peak requirement. So there's two things that we did. This is a project we did with one of our manufacturers, Multistack. And Multistack has some unique equipment, unique central plant heat pump equipment that's helping us achieve our goals here. So what we've done is we've installed two separate heat recovery chiller plants, and I'm in the first mechanical room here right now, and right behind me, if you can kind of see me, I'll try and zoom in on that. So that is our first set of heat recovery, our first heat recovery chiller, and we're calling this the low temperature chiller. So this is a central plant chiller, modular construction. So these arrived on site all in independent modules so that they could be, I think there was a hole in the roof. Yeah, I'm looking at it right now. There was a hole in the roof here, so they were able to crane these in and drop them right down on the equipment pad here. And they put down a couple of these rails. I don't know if you can see that. So these rails are put down, and then they're sort of slid onto the rails one by one and connected together. So it makes it very easy in retrofit applications, because as you can see, look around, this is pretty tight mechanical space. It's not bad. The other one is a little bit tighter, but it is a pretty tight space. And so when we're retrofitting buildings, having something that's modular that you can piece together on site makes life a heck of a lot easier. So this plant that we're looking at here is the low temperature plant. So that means that this is running off of our R410A refrigerant, and it's connected directly into the geothermal loop field that is out beneath the soccer field. I'm just going to try and show you here. I'm going to lose my audio here, but I'm going to show you behind me here is a number of pipes. There's a good view. And that main pipe right there is what feeds back out to the geothermal loop field, and on the other side is the supply from the loop field. So those pipes come in to this low temperature chiller plant right here, and their job, the job of the chiller plant, is really to extract the energy from the geothermal loop and boost it. Actually not that far. It's only on design, it's only boosting it up to about 70 degrees Fahrenheit on the other side of the chiller. So here we have the other, there you go. Here we have is the other piping on the condenser side of the chiller that feeds out to the building loop. So basically what they're doing, the design temperatures of the geothermal loop are 38 degrees in, what did we say? Design temp was 38? 38 entering and 29 leaving. Okay, so at worst case in heating, the geothermal loop field is going to get down to 38 degrees Fahrenheit. This is Dennis from JPII is our tech.
Okay. And our entering for the condensing side, for the heat pump loop, is designed 67 entering and 77 leaving.
Perfect. So worst case conditions, after this thing's been running, the loop field's coming in at 38, leaving at 77. So we're just feeding a little bit of warm water out to the heat pump loop that's existing in the building. Now those heat pumps were replaced, but they had the existing loop already there. So we're just feeding out to that part of the building with 77 degrees, and then those heat pumps are going to extract that energy, and through their individual refrigeration circuits will heat, and when it's flipped over, they'll cool each of the individual zones, the classrooms and such. Now, in a second mechanical room, which I'll show you in a little bit, this heat recovery chiller, actually that 77 degrees that it's feeding to the loop is going to a second heat recovery chiller, which is a high temperature chiller. So it has our 134A refrigerant. Now we needed that to reach 100 and...
So the leaving water from here, on this loop, the loop side I guess, is going to be 70 degrees entering, 60 leaving. And the condenser side, going to the hot side for the water, it's entering is 140, leaving 160.
Perfect. So entering is 140, leaving is 160. So that's some high temperature water for a heat pump system to put together. So that's why we needed, it's kind of like a double compressor system where we're using cascading, right? So we're using compressor energy from this low temperature plant, adding that into our building loop, and then the second high temperature chiller is taking it and boosting it even further to 160. Now, the reason why we needed 160 is because this is an existing school. It's an older school. I think it had some major retrofits in the 90s, but it's an older school. So there is perimeter heating, high temperature perimeter heating system. So high temperature rads throughout the school as well. So we needed that 160 degree water to feed to those rads to ensure they had enough heating capacity to meet the building load. And then our final piece of our part of the project was 4 rooftop water source heat pump systems, which the rooftop water source heat pumps are operating on the cold side or the low temperature side of the system as well, and they're providing heating and cooling and fresh air to a few of the automotive shops in the school. So
To my understanding, this building is Canada's first school zero carbon retrofit. And so it's very exciting to be a part of this project to display the technologies that JPII and Multistack can put together for any style of building to switch it and convert it to a zero carbon heating plant. Now, we do have the backup boiler system in there for backup needs, but for predominantly throughout the year, we're going to be operating off of zero carbon geothermal heating and cooling. Okay, now I'm in the East Mechanical Room at John Paul II, and we're at the second heat recovery chiller plant here that Multistack has. And this one is a 4-module plant, and it is the high temperature plant. So it is running off of R134A refrigerant, and its job is to boost the building loop temperature, the 70 or 77 degree building loop temperature, boost that up to 160 degrees. And you can see these modules are a little bit smaller than the previous, but we have one extra module here. So it's based on the capacity requirement of the high temperature loop in this building, which again is perimeter radiators, and then perimeter radiators, yeah. So we're just getting ready to start these up. You can see down here we have our pumps into the chillers. Everything's all set up and running. The key here though is to get enough of a load on the building when you're starting it up to get a good run cycle out of this equipment. So that's what we're working on right now, is just getting that load up, and they'll be ready to start this up shortly.
Allows you to have a heat exchange inside of the...
So Dennis and I are just here talking about the setup of this particular Multistack heat recovery chiller. It's a little different than the one we looked at over in the other mechanical room. This one has something called total access design. Dennis, can you tell us a little bit about what that is?
For this particular model, the total access allows you to isolate an individual circuit from the rest to complete maintenance on it, or some kind of repair where you don't have to drain the entire chiller. You could just isolate it, release, open the Victolics, and drain that one circuit, complete your repairs. In the event you have to drain the water. Normally, these pipes would be installed in here when you don't have the extended headers, and they're just tucked in, and your profile becomes just the outside frame, and everything is tucked inside. But in this case, we have it spread over, and the heat exchanger we're using is a dual circuit. That means you got 2 different circuits going through one heat exchanger, having one common water source, rather than having 2 individual. As well, on the evaporator and condenser side are designed the same way on this application. I believe that's because of the capacity of the heat exchanger. You can get more out of the big one.
Now we had one other thing optional on this chiller here is you can see, sorry that was a really bad shot. You can see on this chiller we have panels here, these gray panels. Okay, so they have an acoustical material on them. They're for sound reduction. So when we start this chiller up, everything's kind of still opened up. But when it's in normal operating, these panels will all enclose the chiller and the compressors to help reduce sound.
Another thing we can mention on this chiller, because it's a dedicated heat recovery, both the condensing and the evaporator side are both insulated everywhere, not to lose any heat from the system while it's operating minus the compressor itself.
Now, can you tell me just a little bit, what makes this chiller a heat recovery chiller? What's the definition basically of a heat recovery? Because this is kind of similar to a heat pump in some ways, but what's the difference between this and...
With the heat pump, you can change this. The difference is from a regular circuit to a heat pump. Obviously, we have a 4-way valve that allows you to switch your evaporator and condenser back and forth depending on your operation mode. With a heat recovery, you're staying within a certain parameter that you're constantly heating. So in this case, this heat recovery chiller has the 134A refrigerant in it that allows it to go to higher temperatures than a 410A system could. And you're constantly creating heat to be used somewhere in the building, and at the same time, you're, again, cooling down the water to be utilized for cooling somewhere. So you're effectively transferring energy either in the heat pump you're taking that heat from the ground or another source.
Okay. So we can essentially control to either the condenser or the evaporator with the heat recovery chiller.
Yeah, and if once we have our design parameters, we log that information into our microprocessor, and it monitors the water coming in and out both on the condenser side and evaporator side, and it decides how much percentage. For example, over here you have 84 demand for heating and nothing for cooling. That could be because of there's no demand, or there is no pumps on right now. Once there is a demand, then we can start transferring energy from one area to another. There has to be enough energy to be transferred from the cooling side to the heating side to be running. So in our case, it's 25% minimum.